So section 6.6 is a section titled Logarithmic and Exponential Equations. Every problem in this section is going to have an equal sign, and we're going to solve, I think, for x for all the problems. For each of the problems, we're going to get an answer for x. Some of the equations are going to be exponential equations. Exponential equations, you can identify them because there's an x and an exponent. And the other kind of equations, logarithmic equations, they're easy to identify because they have logarithms. Exponential equations have two main ways that can be solved. Exponential equations can be solved with logarithms, always. Can be solved using logarithms 100% of the time. And in special cases, they can be solved by rewriting each side to have the same base. The first 16 problems are set up so that this method will work. But in general, if I have an equation that has an x with an exponent, 100% of the time I can solve that equation with a logarithm. And some of the time I can solve those equations without logarithms. The first 12 problems could actually be solved without logarithms, and I'll show you how to do it. So, to solve the equations in problems 1 through 12 by the way that's kind of described, writing each side of the equation with the same base and equating the exponents, and then it says problems may also be solved with logarithms. Let me show you what this first sentence asks me to do. The first sentence wants me to write each side with the same base. In problem 2, on the left-hand side, the base is 3, and the exponent is x. On the right-hand side, the base is 27. The exponent's 1. That's not going to be so interesting. I'm going to write each side with the same base. And there isn't much I can do on the left-hand side because the base is a prime number. So there must be a way to rewrite the 27 so that its base is 3. And I'm going to do that by making a prime factor tree for 27 and then writing 27 as a power of 3. So a prime factor tree for 27, you'd get started by making a 27 with a v under it, essentially, upside down v. And then on the bottom of that v, you're going to write any two numbers that multiply out to be 27. If a number is prime, you're going to circle it. If a number is not prime, you're going to make a branch and do the same process to that number. So for this 9, I'm going to make a v under it and write the two numbers that multiply to be 9 that are 1, essentially, a 9. So this tells me that 27 is equal to 3 times 3 times 3, which is 3 cubed. So I can rewrite this problem as 3 to the x equals 3 cubed. Now, on this side, the base is 3, and the exponent is 3. In an exponential equation, an equation that has an x and an exponent, if it's possible to write each side with the same base, then we can drop the bases and set the exponents equal to each other. So my next step after getting both sides written with the same base is I'm going to drop the base of 3 and set the exponents equal to each other. And that's actually going to give me the answer because the exponents, when I set them equal to each other, so I'm going to cancel those 3's out, set the exponents equal to each other. Because the left exponent is just a plain x, that's actually going to be the answer for all of the problems in this section. Because we're solving a problem that has an equal sign, we can check. And if I want to check, I should take the answer and plug it in for that x and make sure that the left side simplifies to be the right side. So the answer is x equal to 3. If I plug a 3 in for that x, I should know that 3 cubed is 27 because I just figured that out. But on my calculator, I can simplify, go 3 up arrow 3. and that's going to give me 27. So both sides, if I put 3 in for x into the original problem, simplify to be the same number, so I know my answer is correct. This problem could also be solved with logarithms, but it was so easy to do without logarithms that it's probably not really worth introducing logarithms until the problems get a little bit harder. So your problem 1 could be solved real similarly, and you might be able to look at problem 1 and know the answer. If the problem's easy enough that you can look at it and know what the answer is, then you don't have to show any work. It's okay to just be clever enough to look at a problem and know the answer. I know the answer to problem 4 without doing any sort of algebra, and I could just write down an answer, but I'm going to do it using the same method that I use for number 2. On the left-hand side, the base is 3, the exponent is x plus 2. Because this base is a prime number, it's kind of hard to rewrite the left-hand side any better. On the right-hand side, the 81's not a prime number, so I'm going to make a prime factor tree for it. I'm going to write 81 equals 9 times 9. Neither of the 9's are prime, so under the 9's I'm going to make a couple of branches, and each of the 9's is 3 times 3. So 81 is equal to 3 times 3 times 3 times 3, which is 3 to the 4th. So I can rewrite problem 4, leaving the left-hand side 3 to the x plus 2, changing the right-hand side to 3 to the 4th. And if in an exponential equation you can get both sides written with the same bases, then you can drop the bases and set the exponents equal to each other. When I do that this time, I don't have my answer yet. I just have to do the one more step to solve for x by minusing 2 from both sides. So all I'm doing for each of the first 12 problems is I'm doing the algebra necessary to make each side have the same base. And once I can get both sides written with the same base, then I can drop the bases and set the exponents equal to each other. I can check all of these, and if I wanted to check problem 4, I would just take the 2 and plug it in for that x on the left-hand side and make sure that 3 to the 2 plus 2 power equals to 81. I can do this all on my calculator. I could do it in my head. If I want to do it all on my calculator, the left-hand side, I'd go 3 up arrow, parentheses 2 plus 2. I need to put the entire exponent in a parentheses if I want to check the whole thing on my calculator without adding the 2's in my head. And when I hit enter, I get 81 for the left-hand side, which is exactly what the right-hand side is, so I know that my answer is correct. So every problem in this section we can check. And for exponential equations, it's not such a big deal if we don't check. But when we get to logarithmic equations, if we skip the checking, there's some of the algebra that we do for logarithmic equations that produces solutions that don't check, and so it's going to be important to check. So you should be able to do 3. Problem 6 might be one where it might make sense to use logarithms, because I have the ugly fraction bases, a fraction base on the right-hand side, a left-hand side, and that's not my friend. So I'm going to solve it both ways. I'm going to solve it using the same strategy that I did for problems 1, 2, and 4, and then I'll solve it using logarithms. So I'll solve it first by making each side have the same base. That fraction is not helping me at all. I need to use a rule that we have for negative exponents. And the rule that's going to be needed for numbers 5 and 6 would say that 1 over x to the n power equals x to the negative n power. And for my problem 6, the inside of the parentheses is really 1 over 3 to the first power, and I can rewrite that as 3 to the negative 1 power using this rule. 3 to the negative 1 power is equal to 1/3. In fact, if on my calculator I type 3 up arrow negative 1 power and then hit math and enter twice, I see that 3 to the negative 1 power is 1/3. So I'm going to rewrite the left-hand side so it doesn't have that fraction base. Inside the parentheses, I'm changing the 1/3 to 3 to the negative 1 power. On the right-hand side, I'm going to change the 27 to 3 cubed, and I already figured out that 27 was 3 cubed, so I'm not going to do that prime factor tree again because I have that at my fingertips. Now both sides have the same base, but the left side has a parentheses, and to clear this parentheses, when you have one base that has two exponents that apply to it, to clear the parentheses, you have to multiply the exponents. So I'm going to multiply the exponents and get 3 to the negative 1 times x equals 3 cubed. Now I have both sides written with the same base, and there isn't a parentheses on either side, so I can drop the bases and set the exponents equal to each other. When I set the exponents equal to each other, I get negative 1x equals to 3, and now I'm just going to divide both sides by negative 1, and I get x equal to negative 3 for my answer. I should check it because I can. In a second, I'll solve it using logarithms, just in case you want to use logarithms. To check it, I should go 1/3 to the negative 3 power, putting negative 3 in for that x, and it should equal 27. On my calculator, I'm going to have to go parentheses 1 divided by 3, parentheses up arrow negative 3, and that should equal the 27. So on my calculator for the left-hand side, I need to do that. So real quickly, parentheses 1 divided by 3, parentheses up arrow negative 3, and when I hit enter, I get 27, so I know that that answer is right. The other way I can solve this problem is I could take the log of both sides. And when I take a log of both sides to solve a problem like this, I'm probably locked into using my calculator. So the initial problem said 1/3 to the x equals 27, and the way that I solved it was completely right. If you didn't remember this rule, eventually we're going to learn how to solve these problems with logarithms, and the way to solve a problem that has an x and an exponent with logarithms is to take the logarithm of both sides. Usually I take the logarithm base 10 because that's one of the bases my calculator can do. After I take the logarithm of both sides, if that's the way I want to solve this problem, I'm going to make the exponent into a coefficient by using that third rule of logarithms that we learned in the last section. So I can rewrite this as x times the log of 1/3 equals the log of 27. My calculator is really picky about the parentheses. I'm going to temporarily put that 27 in a parentheses because I know that's what I'm going to need to do on my calculator. Now I'm going to solve for x. The x on the left-hand side is being multiplied by that logarithm, so to get the x detached from that logarithm, I need to divide it on both sides. On the left-hand side, when I do the division, I cancel out the logarithms. I'm left with the x. And on the right-hand side, I'm going to use my calculator. And on my calculator, I'm going to do log of 27 for the numerator, and then a division sign for the fraction bar, and then log of 1 divided by 3. Both the logs are in base 10, so I don't really need anything more than just basically entering what I see there on the right-hand side. I know the answer is negative 3, so I better get negative 3 when I do this. So log of 27 divided by log of 1 divided by 3. And this gives me x equal to negative 3. Exactly the same answer solving with logarithms as we get by making the bases the same. All the problems that are exponential equations can be solved using this strategy, using logarithms. Only really specially constructed problems can be solved by making the bases the same. Let me do 7 because 64 is a big prime factor tree. So I'm going to solve this making each side written with the same base. I'm going to do a prime factor tree for 64. 64 is 8 times 8. Neither of the 8's are prime, so I'll branch under both of those. Both the 8's are 4 times 2. The 2's I'm going to circle because they're prime. The 4's I'm going to branch again. and both of the 4's are 2 times 2. The prime factoring for 64 has 1, 2, 3, 4, 5, 6. 64 is 2 to the 6th power. So if I'm solving problem 7, I'm going to say this can be written as 2 to the 4 minus x equals 2 to the 6th. Now that I have both sides written with the same base, I can cancel out the bases and set the exponents equal to each other. When I do that, I'm going to sneak a 1 in front of the minus x. So I'm going to write this as 4 minus 1x equals to 6. It's going to make my work easier to follow, I think. Finish up to solve this for x. I'm going to minus 4 from both sides and get minus 1x equals to positive 2. And then divide both sides by minus 1 and get x equals to minus 2. And that would be my answer for problem 7. To check it, I just need to go 2 to the 4 minus negative 2, and that needs to be 64. I'll check it on my calculator because it's easy enough to do. So 2 exponent 4 minus, 4 minus negative 2 parentheses. And when I hit enter, it has to give me 64 because the right-hand side is 64, and it does. All right. When we go to do number 9 and 10, the prime number is on the right-hand side. I'm going to leave the right-hand side as just a 3. I'm going to throw the exponent of 1. The left-hand side, I need to do a prime factor tree for 27. And I know 27 is 3 cubed. The 27 already has an exponent, so when I go to do my prime factoring for 27, I should probably put the 27 in a parentheses. Otherwise, I'm going to have 2 exponents next to each other that's going to mess me up. So this will be the 3rd time I dealt with 27. So I'm going to rewrite the 27 inside a parentheses with an x outside the parentheses as 3 cubed. Now I have one base of 3 with 2 exponents that apply to it. To drop the parentheses, you multiply the exponent 3 times x. So the exponent is going to be 3 times x, which is 3x. And that's going to be 3 to the 1st. Now I have the bases the same. I drop the bases and I set the exponents equal to each other. And I'll divide both sides by 3 and get x equals to 1/3 for my answer to problem 10. Let me check. So for checking, I'm going to plug 1/3 in for that x. I get 27 to the 1/3. I want to make sure that that equals to 3. And on my calculator, that 1/3 needs to be in a parentheses. I'm going to go 27 up arrow parentheses, 1 divided by 3, and that should equal to 3. So 27 exponent parentheses 1 divided by 3 does equal to 3, so I know my answer is correct. Your problem 9 will work the same way. Problem 11 is trickier than problem 12, so I'll do 11 for you. So in problem 11, the left-hand side has a base that's not a prime number. If I do a prime factor tree for 16, I'm not going to get this 4. That's the base on the right-hand side. There's a couple ways to do 11. I'll be consistent and I'll make a prime factor tree for 16. When I do a prime factor tree for 16, 16 is 4 times 4, and each of the 4's are 2 times 2. So the prime factoring for 16 is 2 to the 4th power. So I can rewrite the left-hand side as 2 to the 4th power to the x by writing the 16 as 2 to the 4th. The right-hand side is 4, and 4 is not having a base of 2. So I'm going to do a prime factor tree for 4 as well. Because it's not a prime number, I can do a prime factor tree for it. And these problems are set up so that if you do a prime factor tree for any of the non-prime numbers, it'll make both sides have the same base. So I needed to prime factor tree both the number 16 and 4. On the left-hand side, I put the 16 in a parentheses because it had an exponent, and when I prime factored it, I was going to get another exponent, and the 2 exponents needed to be multiplied, and I just separated them with a parentheses to help myself realize that. So I can rewrite this problem as 2 to the 4x equals 2 squared, drop the bases, and set the exponents equal to each other, and then divide both sides by 4. On the left-hand side, you get an x, and on the right-hand side, that fraction reduces to 1/2. I claim that that's my answer. And I should just go 16 to the 1/2 power and check it real quickly. So I'm going to check it just by going 16 up arrow parentheses 1 divided by 2, putting 1/2 in for that x. When I hit enter, it should give me 4 because that's what the right side is, and it does. So that my answer is perfect there. Problems 13 through 24 are not possible to solve using the writing each side with the same base, very specifically, because if I try to write, if I do a prime factor tree for 6, it's 6 is equal to 2 times 3. Its prime factor tree isn't 3 to some power, so I can't do 13 by writing both sides with the same base. Similarly, I can't do 14 with writing both sides with the same base. Each of these problems need to be solved using logarithms, and because my question says round to 2 decimals, I'm going to get my calculator in 2 decimal mode. I'm going to hit the mode button, go down to float, arrow over to 2, and hit equals. Now my calculator is going to give me 2 decimals. I hit second and quit to get out of that screen. I'm going to solve each of the problems in problems 13 through 24 by taking the logarithm of both sides. So I'm going to go the logarithm of 2 to the x equals the logarithm of 10. Notice I didn't put any parentheses in. My calculator is going to want parentheses, and when I get decimal answers with logarithms, I usually use my calculator. I'm going to make the exponent of the x a number in front of that logarithm being multiplied by that logarithm. And now I'm going to divide both sides by the log of 2. On the left-hand side, the logs are going to cancel and be left with an x. And on the right-hand side, I'm going to use my calculator. And on my calculator, I'm going to go log of 10 divided by log of 2. And I'm going to write an answer down. And it's a 2 decimal rounded answer, so it's not going to be like the best answer. It's not going to check as nicely. So my calculator gives me 3.32 for an answer. That's what I'm going to say is an answer. And watch what happens when I go to check in this. When I go to check and plug in 3.32 for x, if I go 2 to the 3.32 power and do that on my calculator, it's not going to equal 10 exactly. This is because the real answer has, 1,000 decimals or 1,000,000 decimals after the 3.32 even. When you're checking a rounded answer, you're going to get a rounded checking. It'll just be kind of close. So for my checking, when I go 2 up arrow 3.32, I can't expect to get exactly 10. I want to get something close to 10. And I got 9.99. That's close enough to 10 for me because I rounded to 2 decimals. This rounds to 10. I feel good about my answer. When we go to do problem 16, because the base on the left side is e, we can certainly take the log of both sides. So on 16, it would be okay to do the log of e to the x equals the log of 1.15. And you get exactly, and in fact, let me do that. And let me do that just quickly here. Make the exponent a coefficient, so I'll get x times the log of e equals the log of 1.15. And then divide both sides by the log of e. And this is going to give me, on the left side, x. On the right side, something I need my calculator for. So on my calculator for the right-hand side, I'm going to go log of 1.15 parentheses divided by log. And to get e without an exponent, you hit second and divide. And my answer I'm going to write down as 0.14. The better way to do this, when the base is e, it's better to ln on both sides. My calculator has 2 bases that it does logarithms with, base 10 and base e. The reason this is going to be better because I'll have less calculator work. So if I take the ln of both sides, that's equivalent to taking the log of both sides. If I took the ln of both sides, I'd still rewrite this as x times the ln of e equals the ln of 1.15. The difference here is on the left-hand side, the ln of e is 1. So on the left-hand side, the ln of second e is equal to 1. So this left-hand side is really x times 1 equals the natural log of 1.15. And it makes it easier on my calculator to do the work because now I don't have to divide, because on the left-hand side, even without dividing, I have the x isolated. So I would just have to go ln of 1.15 on my calculator, and I'll get that same answer of 0.14. Exactly the same answer, better way to do it. Anytime I have an exponential equation and there's a base of e, I'll take the ln of both sides. If the base is anything other than e, I'll take the log of both sides. Both answers should check. To check, I'm going to plug in 0.14 for this x and go second and then ln, type 0.14, and then it actually came out exactly because my calculator is rounding to 2 decimals, so that feels really good for an answer. 17, 18, 19, 20 are tricky because there's a number on the left-hand side that the exponent doesn't apply to. Before I take the logarithm of both sides in 17 and 18, I should divide by the number that's in front of the parentheses that the exponent doesn't apply to. If you don't do this and you take the logarithm of both sides, you can certainly get the right answer, but you'd probably make a mistake. It's pretty tricky to do it correctly if you don't divide by the number on the left-hand side that the exponent doesn't apply to. When I divide on the left-hand side by that 4, the 4's cancel, and it makes it so I don't need the parentheses anymore. Now I'm going to take the log of both sides. On the left-hand side, I'm going to bring the x out front. And then I'm going to divide. On the left-hand side, when I do that division, the logs of 3's cancel. I'm left with my x. On the right-hand side, I'm going to do log of 6 divided by log of 3, and my calculator needs parentheses for those logarithms, so log of 6 divided by log of 3. And I'm going to write down 1.63. And then to check, I'm going to enter 4 parentheses, 3 to the 1.63 power parentheses, and that should equal to 24. And that's just going to the original problem and putting in 1.63 for x. Let me see how that works out. So go 4 parentheses, 3 up arrow, 1.63 parentheses, and I get 23.98 equals to 24. And anytime I have an answer that's rounded, I'm not guaranteed of an exact checking. That's close enough for me. So your 17 should work the same way. 19 and 20 work the same way. There's numbers on the left-hand side that the exponent doesn't apply to. In problem 19, the exponent only applies to the e and doesn't apply to the 32. In problem 20, the exponent only applies to the e. It doesn't apply to the 14. Just like I solved problem 18, I'm going to divide by the number on the left-hand side that the exponent doesn't apply to. On the left-hand side, I'm going to cancel the 14s and get e to the 3x. And on the right-hand side, that's equal to 3. The nicer way to solve this problem now is to take the ln of both sides as opposed to the log base log of both sides, because the base is e on the left-hand side, and it'll just make my work easier. So I took the ln of both sides because the base was e. I'm going to rewrite the left-hand side as 3x times the ln of e equals the ln of 3. And then on the left-hand side, that ln of e is equal to 1. So I'm going to replace this as 3x times 1 equals the natural log of 3. That's going to give me 3x equals the natural log of 3. And then I'm going to divide both sides by 3. I'm going to get x equals the natural log of 3. start putting that 3 in a parentheses because my calculator needs it, over 3. That should be pretty easy to enter. I should enter it just like that, except put a divide sign instead of the fraction. So on my calculator now, natural log of 3 parentheses divided by 3, round it to 2 decimals, I get 0.37 for my answer. So I'm going to write x equals 0.37, and I'm going to check it by plugging it into that original problem, going 14 second and ln, and then 3 times, because there's a 3 up there, and times 0.37. My answer came out to 0.37. And when I do this, I expect to get something close to 42. I got 42.48. That's not terribly close, but it's as close as I'm going to get right now. If I would have carried more decimals, if I had changed this to mode float, and when I did the ln of 3 divided by 3, if I had done this now, I never wrote that for an answer. If I did 14 second ln 3 times and then typed in 0.366, 14 times 0.36620400962. If I want my checking to come out better by putting the answer in for x that I came up with, I can do it a non-rounded answer or a better version of the answer. Whoa. Oh, I should do it 3 times. Let me do that again. I should do, oh gosh, ln of 3 divided by 3. Then for checking, I should go 14 second ln 3 times 0.36620400962. And when I do that, I'll get a perfect checking. So when I'm dealing with rounded answers, my checking is only going to come out so decent. If you're not happy with the checking, you can get a non-rounded answer, or at least an answer that carries as many decimals as your calculator can handle for checking purposes. But I'm going to be content if when I go to check, if my answer is just close. The next few problems I always put on the test, and I hate grading them, so I don't know why I put them on the test. They're exponential equations that both sides have an x in the exponent. These are a disaster to solve. I'm going to start off by taking the logarithm of both sides. So I'm going to go the logarithm of 2 to the x equals the logarithm of 3 to the x minus 1. I'm going to make the exponent a coefficient, or put the exponent out in front of the logarithm. And on the left-hand side, when an exponent has a subtraction or addition in it, it doesn't need a parentheses, but it certainly can have one. When you bring that exponent and shove it in front of the logarithm, it needs to be in a parentheses. So exponents don't usually have parentheses, but when you put an exponent in front of a logarithm that has an addition or subtraction, it has to be in a parentheses to get the right answer. So it took the logarithm of both sides, made the exponents coefficients. That's not new. This right-hand side is new. To clear the parentheses on the right-hand side, I'm going to multiply x times the log of 3, and I'm going to multiply minus 1 times the log of 3. So that's going to allow me to rewrite this as x log of 2 equals x log of 3 minus 1 log of 3, and I'm just going to write minus log of 3. My calculator doesn't need the 1 so much. Now I need to get the x's on one side. I don't set this equal to 0 because there's no x squared. So I'm going to minus x log of 3 from both sides. And it's a little bit tricky to do this. On the right-hand side, when I do this, they cancel. I'm left with the minus log of 3. On the left-hand side, I have to be careful on how I combine these. I have x log of 2 minus x log of 3 when I do this subtraction. On the left-hand side, each term has an x. I'm going to 1 parentheses common factor out a common factor of an x, which means on the left-hand side, I'm going to write 1 parentheses, put the common factor of x in front of that parentheses, and then after I take an x away from each piece, that's what I'm going to write inside the parentheses. So I'm going to write log of 2 minus log of 3. that inside the parentheses can be simplified, and if I simplify it, it makes my calculator work that's coming up easier. If you have two logarithms that have the same base, and there's a minus between the two logarithms, you could write the two logarithms as one logarithm by dividing their arguments. That's using the second rule of logarithms that I had. So inside this parentheses here, two logarithms, both base 10, minus sign in front of them. I made the two logarithms into one logarithm. That's going to make it a lot easier when I get to this next step. Now I'm going to divide both sides by the log of 2/3. I'm going to need parentheses around each of the numbers when I go to use my calculator. On the left-hand side, I'm canceling out the log, so I'm going to be left with an x. And on the right-hand side, it's a calculator activity, and it's not that hard of a calculator activity. So I'm going to go minus, using the minus in the bottom row of my calculator, and then log of 3, parentheses, divided by, and then in the denominator there, log of 2 divided by 3. So only one logarithm for the numerator, one for the denominator. When I get enters, I get 2.71 for my answer. I'm going to check, and when I go to check, I'm going to need to plug in 2.71 on both sides. So for the original problem, I'm going to go 2 to the 2.71 power and see if that equals 3 to the 2.71 minus 1 power, realizing it's not going to check perfectly because of the rounding that I have in my answer. But this is what I'm going to call an answer to problem 22. And let's see how that goes. So left-hand side, 2 up arrow 2.71. Left-hand side comes out to 6.54. Let me do the right-hand side going 3 exponent parentheses. Now on my calculator, that whole exponent's going to need to be in a parentheses, and 2.71 minus 1. And I get 6.54. So these both sides came out to the same number. I feel good about my checking. So your 21 works the same way. We have 23 and 24 left, and then we'll probably make a part 2 to this video. And let me do your 23. You can pause the video and try 23 and then watch me work through it if you want, or you could just watch me do it. So I'll do 23 just because these are hard and I want you to have something correct at your fingertips. So for 23, I'm going to take the log of both sides. I don't need to take an ln of both sides because there aren't any e's in the problem. So I'm going to write the log of 6 to the x minus 1 equals the log of 9 to the x. I have to think of that x minus 1 as being in a parentheses because when I bring it out front of the logarithm, it's going to need to be in a parentheses. So I'm going to rewrite the left-hand side now as x minus 1 times the log of 6. I'm going to rewrite the right-hand side as x times the log of 9. I'm going to do the multiplication on the left-hand side by multiplying x times log of 6 and minus 1 times log of 6 to clear that parentheses. That's going to give me x log 6 minus log 6 equals x log 9. I shouldn't get this equal to 0 because there's not a square. I should get the x's on one side, the numbers without the x's on the other side. And to do that, I'm going to minus x log 6 from both sides. That's going to give me minus log 6 on the left side. And on the right side, it's going to be x log 9 minus x log 6. Just like I did in the last problem, on the side that has the x's, once they're both on the same side, I'm going to one parentheses factor out the x as a GCF. So I'm going to rewrite the right-hand side with a parentheses with an x as a common factor in front of that parentheses. And inside the parentheses, I'm going to have log of 9 minus log of 6. You could actually divide both sides right now and solve for x, but it's going to make the calculator work a lot easier if I rewrite the right-hand side so that it only has one logarithm. And when you have two logarithms that have the same base separated by a minus, you can make them into one logarithm if you divide the arguments. And 9 over 6 I'm going to reduce by 3 to 3 halves. I probably don't really, that's probably being over picky. But since that fraction reduced, I reduced it. Now I'm going to divide both sides by the log of 3 halves. On the right-hand side, the 3/2 with the logs cancel. I'm left with an x. On the left-hand side, all the numbers are going to need to be in a parentheses, and I'm just going to enter this more or less how it looks. So for the left-hand side, I'm going to enter negative log of 6 divided by the log of 3 divided by 2, and get negative 4.42. Claim that's my answer to problem 23. For checking, which is optional but not a bad idea, for checking, I should go that 6 to the negative 4.42 minus 1 equals 9 to the negative 4.42. These could be really ugly numbers in scientific notation. When I check it, I'm a bit worried about what I'm going to get, but I'm going to check them both and then see if I need to make any comments about what we come up with. So if I go 6 up arrow, parentheses, negative 4.42 minus 1, so this whole exponent needs to be in a parentheses. I get 6.06 e to the negative 5. Let me just do the next one. 9 up arrow, negative 4.42. I get 6.06 e to the negative 5. So they do check, and I don't really need to describe what this is. 6.06 e to the negative 5 is my calculator's way of telling me that I was going to have a lot of zeros in the answer that I don't care to write. If you want to get the answer without this e to the negative 5, you need to take the decimal and move it 5 to the left. So I moved it 1, 2, 3, 4, 5 to the left. And any place that doesn't have a number, you put a 0 in. So the number that my calculator gave me, it could have written that. A 4 zeros than a 606. It just makes it easier in some sense, so you're not having to count the number of zeros. Alright, so that's the first part of this section. I don't know if it's easier or harder, it just is the first. And we'll pause and we'll do a second part.